Welcome back, everyone. So in this video, we're going to talk about solving exponential and logarithmic equations. So I'm just going to do equations in this first video, and then in a separate video, I will do inequalities. If I combine everything into one video, it's going to be like 10,000 hours. But anyways, so over here, the notes on the right side, I would say take a second, read through these before you start, but hopefully you already read them. If not, read them. So we're going to be solving these equations whether we're in exponential form or in log form. So when you're solving these exponential or logarithmic equations, first thing you're going to want to focus on is getting your exponential or logarithmic value isolated. So we're still going to be doing your inverse operations, but we're going to focus on getting the exponent value or the unknown value in the exponential function or in the logarithmic function by itself. So to start off, I'm going to add 2 on both sides. We're still doing our inverse ops. So I'm going to have 4 raised to the x equals 7 plus 2, which is going to give us 9. And then if I can't rewrite 4 and 9 or whatever values are on each side, if I can't write them using the same base, what that tells me is I'm going to have to convert to log form. So I'm going to do circle of life. So 4 over to the output of 9 and then back to the exponent of x. So I'm going to rewrite this as log base 4 of 9 would be equal to my x value. So I'm going to flip it because we want the variable on the left. So this would be log base 4 of 9. This would be your simplified value that we want. So moving over to number 2. So same idea, we want to isolate your exponential value that has your variable. So I'm going to get rid of the 5 first. So when I get rid of 5, so we're going to have 2 raised to the x plus 3, and that's going to be equal to 21. So I cannot rewrite 2 and 21 with the same base. So because I can't rewrite using the same base, that tells me to convert to log form. So circle of life, so we're going to have log base 2 of 21, and that's going to equal x plus 3. Now, once again, we still want to get your x value by itself. So I'm going to subtract 3 on both sides. So this is going to be x equals log base 2 of 21 minus 3. Now, what you've got to be very careful about, because this is your answer right here, but what you've got to be very careful about is that we're taking log base 2 of only the 21, not 3. So if you were to rewrite this as log base 2 of 18, you would get that wrong. So we cannot combine 21 and that negative 3. You have to leave them separate. All right, number 3. So we want to isolate 4e raised to the x. So I'm going to start by subtracting 3. So that's going to give us negative 10, which is going to equal negative 4e raised to the x. And then in this case, I now need to get rid of the negative 4. So I'm going to divide both sides by negative 4. So doing that, we're going to have negative 10 divided by negative 4, which is going to give us positive 5 halves equals e raised to the x. Now, I can't get the same base on both sides, so what's going to happen is I need to convert to log form. And then because we're going to have a base of e, that tells us that we're going to use a natural log. So I'm going to have a natural log of 5 halves is equal to x. So then just flip it over. So x equals natural log of 5 halves. Ta-da. All right, now we're going to move on to some logarithmic equations over here. Now with log equations, we have restrictions in place because of your vertical asymptote. So when you get your answer, you're going to check for what are called extraneous solutions, which I'll get to that when we actually get to the answer. So once again, it's going to be the same techniques. You're still going to want to isolate your logarithmic value first. So to start off, I'm going to subtract 4. So we're going to have 2 times log base 3 of x plus 3. And then that's going to equal 6. And then I want to get rid of the 2 in the front, so I'm going to divide both sides by 2. So now we're going to have log base 3 of x plus 3, and that's going to equal 3. So when you get here, Now I'm ready to rewrite in exponential form because I want to get my variable out of the argument. So I'm going to do 3 raised to the third power is equal to x plus 3. So x plus 3 is going to be equal to 3 raised to the third power. So 3 raised to the third power is 3 times 3 times 3, which is going to give me 27. So x plus 3 is going to equal 27. And then subtract 3 on both sides, so we're going to get an x value of 24. So I boxed this answer, but I still need to come up here and actually plug it in because we got to check for extraneous solutions. So to check, you're going to plug it in for your x value up here, and we're checking for any negative values. So if I plug in, we do 24 plus 3, that's going to give us 27, which is a positive number, which means we're good. If we get a negative number, that means that this would be extraneous and it wouldn't work. But because when I plug it in, we get a positive number, that tells me it works. So 24 is a legit solution. So now moving over to number 5, we're going to do the same idea. So I have a logarithmic equation, which tells me I am going to have to check for extraneous solutions. So start by subtracting 2, subtracting 2. So log base 5 of 2x minus 1 is going to be equal to 2. Now I want to do circle of life. So 5 raised to the second power would be equal to argument. So we would have 5 squared equals 2x minus 1. So 5 squared, which is 25, equals 2x minus 1. Add 1 on both sides, so we have 2x is equal to 26, and then divide by 2, so we get an x value of 13. So before I just say all good and dandy and move on, you need to plug it in and make sure that we get a positive number in the argument. So 2 times 13 is 26. 26 minus 1 is going to give you 25. So we get positive 25 in the argument. We're good. So long as it's not negative, we're good. All right, number 6. So I have natural log of 2 minus x divided by 5 equals 1. So I need to isolate my natural log equation, or expression rather, first. So I need to get rid of this 5 in the denominator. So because I'm dividing by 5, I'm going to multiply both sides by 5. So I'm going to rewrite this as natural log of 2 minus x equals 1 times 5, which in this case is 5. Now I can't rewrite, I can't rewrite, I'm going to convert. So when I get here, my natural log is going to have a base of e. So when I do circle of life, e raised to the 5th power is going to equal 2 minus x. So e raised to the 5th is 2 minus x. And then we're going to solve for x. So of course there's multiple ways you could do this. I'm going to subtract 2. So when I rewrite, we're going to have negative x equals e to the 5th minus 2. And I still need to get rid of that negative 1. So you can either divide both sides by negative 1 or multiply both sides by negative 1. So you're going to get x is equal to negative e raised to the 5th plus 2. So another way of writing this would be 2 minus e raised to the 5th. I know in AP world, typically we don't like starting off a value with a negative if possible. So even though they're equivalent, they may be written either way. So either could be expected, either would be taken. All right, moving on, 7. So with number 7, now I see I have logs on everything. So when you see logs in multiple places, that tells you that you're going to be doing log properties. So on the left side over here, because I'm adding these log properties, or log values rather, I'm going to consolidate and condense, and I'm going to multiply the arguments. So that would be product property. So log of 3 parentheses x plus 4. And that's going to be equal to the right side, so log of 5x minus 2. And then once you have log bases on the same side and they have the same base, then what you can do is we're going to take the arguments of both of these logs and we're just going to set them equal. So I'm going to have 3 parentheses x plus 4 equals 5x minus 2. So when I say this, some people like to say, oh, the logs just cancel out. Be very careful when you say cancel, because if you say cancel, then you're technically going to change the problem as if the logs never existed. So rather than say cancel, I would say we're only going to look at the argument. So we're only going to look at a component of the problem. So when you get here, So distribute your 3. So 3x plus 12, which would be 5x minus 2, and it's just algebra 1 from here. So that'd be 14 equals 2x, and then the next value of 7. So before I circle the answer, I'm going to plug it in to all my log values that have a variable. So my 3 logs over here, I don't have a variable over here, so I'm not even going to worry about this one. But I do have variables in the second log and in the third log over here. So if I were to plug in 7 plus 4, that gives me a positive number, I'm good. 5 times 7 is going to give me 35, minus 2 is going to give me 33. It's positive, it's good. So what that tells me is x equals 7 is a legit solution. So number 8. So when I get here, so I have natural log, and then I'm subtracting these 2 logs. So when I subtract, I'm going to do quotient property. So I'm going to condense and do natural log of x plus 1 over 3x minus 5, and that's going to be equal to the natural log of 7. Let me rewrite this. This is getting a little ugly. X plus 1 over 3x minus 5 equals natural log of 7. There we go. That's better. So now that we have the same base of logs on both sides, I'm going to set my arguments equal to each other. So I have x plus 1 over 3x minus 5 equal to 7. So x plus 1 over 3x minus 5 equals 7. So when I solve, I'm going to multiply both sides by 3x minus 5. So that's going to leave me with x plus 1 equals, and I'm going to go ahead and distribute over here. So that would be 21x minus 35. And then when I rewrite, so I'm going to subtract x on both sides and then add 35. So this would be 36 equals 20x. And then when I divide, we're going to get 36 divided by 20, which when you when you divide, we're going to get 9/5. So I'm going to take that 9/5 and I want to plug it in, of course, in my arguments of my my natural logs over here, and I want to see if I get a negative. So 9/5 plus 1, that's positive, I'm good. 3 times 9/5, it's going to give me, is that 27/5? Over that, that's definitely bigger, so we should be good. So that's positive, yeah. Okay. I'm just going to keep doing a lot of these problems just to hopefully kind of get some practice. Let's actually jump over to, yeah, number 9's a good one. Okay, so with number 9, so once again, I'm adding these values. So that means both of these logs, when I consolidate, I'm going to multiply them in the argument. So log base 3 of x plus 2 times x minus 3, and then that's going to be equal to log base 3 of 14. So now that the log bases are the same, I'm going to set the arguments equal. So I've got x plus 2 times x minus 3. That's going to be equal to 14. So when I multiply it out, we're going to get x squared minus x minus 6 equals 14. And then I want to move everything from the right side over to the left side so that I can factor. So I'm going to subtract 14 on both sides. So that's going to leave me with x squared minus x minus 20 equals 0. So now I can factor this quadratic. And if you can't factor it, then you're going to have to do quadratic formula. So this would be x minus 5 and x plus 4, which means my x values would give me -4 and +5. Now I got to check both of them. So if I plug in -4 into my arguments, so -4 plus 2, that's going to give me a -2. We can't have a negative in the argument. So if it's negative and even just one argument, then it doesn't work. So that tells me that -4 here is extraneous. It doesn't work. So I'm going to disregard the -4. Now when I plug in the 5 plus 2 gives me +7, I'm good. 5 minus 3 gives me +2, I'm good. So the only one that technically works here would be an x value of 5. That's it. If you tell me -4 is a solution, that would be points off. All right, and then let's look at, let's do 11. So with this one, so same idea, I'm going to subtract. So I'm going to do log base 4 of x divided by, hold on, I'm getting ahead of myself. I should have done power property first. So I'm going to rewrite the coefficient of 3 as an exponent of the argument of 2 here. So log base 4 of x minus log base 4 of 2 cubed is going to be equal to log base 4 of x plus 7. So now I'm going to have log base 4. Now I'm going to do quotient property. So since I'm subtracting these values, I'm going to divide them in a single log. So x over 2 to the third power, which is going to be 8. And that's going to be equal to log base 4 of x plus 7. So now my log bases are the same. I'm going to set my arguments equal. So x over 8 is equal to x plus 7. So I'm going to multiply both sides by 8. So that's going to leave me with x equals 8x plus 56. Then I'm going to subtract the 8x over. So that's going to give me a negative 7x equals 56. And then when you divide, we're going to get an x value of negative 8. So of course, we're in a log equation over here. So I have to check my log values where I have a variable. So if I were to plug in that negative 8 up here, we get a negative value, which means it can't work. So the one and only potential solution we have here is extraneous, which means we have no solution in this case. All right, and then 10 and 12, I will let you guys try on your own. I will say 10, if you want to try this one, you should get an x value of 3e squared. And then for number 12, you should get no solution if you want to try these on your own. All right, now we're going to move on and do some exponential equations. So I want to solve these equations. So what we're going to do is we're going to look at our exponential equations, and we want the bases to be the same. Once the bases are the same, then we can set the exponents equal. So if I look at 13 here, we already have a base of 2 on both sides. So I'm just going to take my expressions on both sides and set them equal. And then I'm going to solve. Now, the beauty about exponential functions is there's no domain restrictions in exponential functions, so I don't have to worry about extraneous solutions in this case. So when you get here, it's just straight up algebra. So subtract 2x on both sides, so we get 3x equals, then we're going to add 1 on both sides, which gives me 8. And then divide by 3 on both sides, which gives me an x value of 8/3. So for an exponential function, it's tried and true, it's good. So 14. So the key idea here is we need to get the base values to be the exact same. So if I have 8 and 2, I can rewrite 8 with a base value of 2. So I'm going to rewrite it as 2 raised to the third power. And then I still have 3x minus 2 on the exponent. And then over here, I left this alone, so 2 raised to the x plus 5. Now what's going to happen, now that we have the same base, I'm going to set my exponents equal. So how you're going to write that left side is this is going to be 3 parentheses 3x minus 2. And that's going to equal x plus 5. So I'm still setting the exponent equal. I'm just going to have to do distributive property. So when I do distributive property, so we get 9x minus 6 equal to x plus 5. So subtract x on both sides, so we get 8x. And then add 6 on both sides, so we get 11. Then divide by 8, so we're going to get 11/8. And we're in an exponential function, so I don't need to check for extraneous, so it's good to go. 15. So with 15 here, so I have a base of 9 and a base of 27. Both of these values I can rewrite as a base of 3. So I'm going to rewrite the left side as 3 squared and then raised to the 2x, And then 27, I can rewrite that as 3 cubed. So 3 raised to the third power. And then that's going to be raised to the x plus 2. So now that I have the same base, now I'm going to take these exponent values and set them equal. So I'm going to have 2 times 2x equals 3 parentheses x plus 2. So we're going to have 4x equals 3x plus 6. Subtract that 3x on both sides, so we get an x value of 6. Ta-da. 16, I would invite you to try this one on your own. So what's going to happen here is I need to rewrite 1/2 and 4 using the same base. So I'm going to rewrite 1/2 as 2 raised to the negative first power. That way I have a base of 2. So I have 5x plus 7. And then because I have a base of 2 on the left side, I'm going to rewrite 4 with a base of 2. So this would be 2 raised to the second power. And then, of course, that would be raised to the x. So now I'm going to set my exponents equal. Oops, there we go. So this would be in negative parentheses 5x plus 7 equal to 2x. So when I distribute the negative, so we've got negative 5x minus 7 is equal to 2x. Add the 5x on both sides, so we've got negative 7 is equal to 7x. And then divide, and we have an x value of negative 1. Ta-da. All right, and then these are going to be just renditions of what we've already done, so I'm going to skip over these, but I do want to skip down to factoring. So factoring, this still falls under the category of rewriting, because we're going to rewrite it in a different way. So with 21, so I want to be able to rewrite both of my exponent bases as the same value. So I can rewrite 9 with a base of 3. So I am going to rewrite this as 3 squared raised to the x plus 3 raised to the x. Now what's going to happen, so I'm going to rewrite this in a different way to kind of hopefully make this a little bit more clear. With your exponents, or rather with multiplication, the order of your multiplication doesn't matter. Meaning, if I do 2 times x, it's the same as doing x times 2. So what can happen is I'm going to rewrite this as 3 raised to the x and then squared plus 3 to the x. Now what I want you to notice is how we have 2 3 to the x's in the first term, and we have 1 3 to the x in the second term. So what I want you to notice is in both terms, I can factor out 1 3 to the x. And when I take it out, that's going to leave me with just 1 3 to the x plus 1. So if I were to redistribute, we're going to get this answer up here. So right here, this would be our final answer. 3 to the x times 3 to the x plus 1. That would be our factored form. So same idea with 22. I would say pause here, try 22 on your own. So if I have a base of 8 and a base of 4, I can rewrite both of these using a base of 2. So I'm going to have 2 to the third power and then 2 to the second power raised to the x plus 2 squared, all raised to the x. And then same idea as before, I'm going to switch the order just to kind of help us visualize it a little bit more. So this is going to be 2 to the x 3 times plus 2 to the x 2 times. So when I look, I have it 3 times over here, 2 times over here, so I can take out 2 of them. So when I take out 2 raised to the x squared, I'm actually taking out 2 raised to the 2x, since I'm taking 2 of them out. So that's going to leave me with 2 to the x plus 1. So this is one way of writing it. However, I could technically keep going and factor it, or not factor it, but I could rewrite it in a different way. Meaning, if I have 2 squared, that's the same as writing it as 4 raised to the x times 2 raised to the x plus 1. So either one of these methods or answers would be plausible. All right, 23. So same idea, we still need to get these values to have the same base. So I can rewrite 4 as a base of 2. So this would be equal to 2 squared raised to the x minus 2 raised to the x minus 12. So once again, I'm going to flip the order just to give us a visual. So 2 to the x all squared minus 2 to the x minus 12. And then what happens here, or what I find is most helpful for everyone, is when you get here, I would recommend doing a substitution. So I'm going to say n is equal to 2 to the x. So when I sub, so that means, let's do this. Let's make sure I color code. So that means we're going to get n squared minus n minus 12 when I do my substitution. So when you get here, now it's just a simple factoring problem from your Algebra 1 days. So when you factor, so I want factors of negative 12 that add up to negative 1. So that's going to be n minus 4 and n plus 3. Then when you get here, once you factored it, then you're going to take your n value and you're going to plug it back in to your equation. So then when I rewrite, we're going to have 2 raised to the x minus 4 times 2 raised to the x plus 3. So this would be your factored form. All right, now 24. So this one's going to be a little bit more tricky because now we've got some more exponents over here. So I'm going to expand it first. So I'm going to deconstruct my product property. So I'm going to have 2 raised to the 2x times 2 squared minus 5. So over here, I'm going to deconstruct my exponents over here and give each of those values their own base. So I'm going to rewrite this as 16 raised to the x plus 2 squared, which is going to be 4. So 4 times 2 raised to the 2x. Well, actually, 2 squared, or 2 raised to 2x, I'm going to rewrite that as 4 to the x minus 5. Now, when you get here, you want 16 raised to the x and 4 raised to the x. These need to have the same base. So you could do it either with a base of 2 or you could do it with a base of 4. I would recommend the higher the base value, the better. So I would recommend writing it as a base of 4. So I'm going to rewrite 16 as 4 squared raised to the x plus 4 times 4 raised to the x. Well, I'm not changing this at all. Minus 5. So once again, I'm going to rewrite. So this would be 4 to the x squared plus 4 times 4 to the x minus 5. So I did not need to rewrite that in red, but it's okay. So when you get here, I'm going to do my substitution. So I'm going to say n is equal to 4 raised to the x. So with substitution, that tells me I'm going to have n squared plus 4n minus 5. So when I factor, I want factors of negative 5 that add up to positive 4. So I want n plus 5 and then n minus 1, which means when I plug back in, we're going to have 4 raised to the x plus 5 and then 4 raised to the x minus 1. So this would be what we want. So now that one was a little bit more tricky. So speaking of tricky, my personal faves. So now we have 6 raised to the x plus 5 times 3 raised to the x minus 2 times 2 raised to the x minus 10. So this is just a giant factoring problem. So what's going to happen is notice how we have 3 different base values. So what I want to do is I want to deconstruct the first value using the multiple or using the values of my others. So I can rewrite 6 as 3 times 2. So that's what I'm going to do first. So I'm going to rewrite as 2 times 3 raised to the x plus 5 times 3 raised to the x minus 2 times 2 raised to the x minus 10. Now what's going to happen here is I want to rewrite this as 2 to the x times 3 to the x plus 5 times 3 to the x minus 2 times 2 to the x minus 10. Now when you get here, this is where I want to turn it into grouping. So I'm going to group the first two terms together, and then I'm going to group the last two terms together. So when I do this, out of the first group in blue, what I have in common is a 3 to the x. So I'm going to factor that out. So when I factor out 3 to the x, that's going to leave me with 2 to the x plus 5. And then in the second group over here in purple, I'm going to factor out a negative 2. So when I factor out negative 2, that leaves me with 2 to the x plus 5. Now remember, the values in parentheses here, they have to be the same in order to be able to do the next step. So what's going to happen here is now we're going to do another greatest common factor. I'm going to factor out 2 to the x plus 5. So when I factor it out, so 2 to the x plus 5, and then I'm left with 3 to the x minus 2. So this would be your factored form. So with that, I would invite you to try number 26 on your own. All right, and then down here, 27 through 30, these are going to be some higher level questions. So I have these saved for some higher level types. So now we're going to solve the exponential or logarithmic equations, but now the bases can't be rewritten using the same value. So what's going to happen is if the bases can't be rewritten, what you're going to do is you're going to take the log of both sides and then do power property. So when I take the log of both sides, your power property tells you your exponent is going to become a coefficient. So I'm going to do log of 2 raised to the 4x plus 1 equals log of 3 raised to the x. Now, when I take the log of both sides, remember, what you do to one side, you got to do to the other. So I can just take the log of both sides. So when I do this, power property tells me move your exponents to coefficients. So I'm going to have 4x plus 1 times log of 2. And then that's going to be equal to my new coefficient of x times log of 3. And when you get here, you're going to be solving for your variable, which is in multiple places, unfortunately. So what's going to happen is in order to get your variable on one side, I need to distribute my log of 2. So this is going to turn into 4x log of 2 plus log of 2 times 1, which is just log of 2, equals x times log of 3, which you don't have to have that multiply there. You can just leave it. It's up to you. Now, when you get here, then what has to happen is I need to get all my x values on the same side of the equation. So what I'm going to do is I'm going to move 4x log of 2, I'm going to move it to the right side over here. So when I subtract, I'm going to have log of 2. It's going to be equal to x log of 3 minus 4x log of 2. And now that I have an x value on both sides, what I'm going to do is I'm going to factor it out. So doing that, we're going to have log of 2, and that's going to be equal to my x value, and then what I have left is going to be log of 3 minus 4 log of 2. And then if I want to get my x value by itself, I'm going to divide by log of 3 minus 4 log 2. That is crooked. Why are you... There we go. So I'm going to divide by log of 3 minus 4 log 2 on both sides. So my x value in this case is going to be log of 2 over log of 3 minus 4 log of 2. And of course, there's multiple ways that we could rewrite the same thing, so just keep that in mind. Like, for example, I could make this 4 go up here, make it 2 to the 4th power, and I could do log of 3 minus log of 16. So I could rewrite that denominator like that if I wanted to. Okay, and then number 28 is the same idea. I would say if you want to try it on your own, but your answer when you get to your final answer, I'll write out the answer so you can at least check it if you need to. So that'd be log of 5 plus 3 log of 4 over 2 log of 4 minus log of 5. And then, of course, any equivalent representation, so you could also rewrite it as log of 5 plus log of 4 to the third power, which would be 64, over, then, of course, log 4 squared, which would be log of 16, minus log of 5. So either of those would be accepted. So if you want to do that one, I check it. Okay, 29. So now looking here, so I have log base 8 of 16 and log base 2 of x. So now your log bases aren't even the same. So when you get to a problem like this, you're going to have to do a change of base. So what's going to happen is you want to ask yourself, would it be easier to change 8 to a base of 2, or would it be easier to change 2 to a base of 8? Well, I'll tell you. Changing 8 to a base of 2 would be way easier. So what's going to happen is I want log base 2 of something over log base 2 of something. So let's do this. So my new base for this log is going to be 2, and I want to write the original argument and the argument of my numerator, and then I want the old base to be the argument of my denominator. And then that's going to be plus log base 2 of x equals 10/3. And then you want to look to see, can I actually evaluate any of these values? So log base 2 of 16, this is the same as asking 2 to what power gives me 16? Well, that would be 4. And then same idea in the denominator, I have log base 2 of 8, so 2 to what power is going to give me 8? Well, that's going to be 3. So I'm going to rewrite that entire value as 4/3. So 4/3 plus log base 2 of x is going to be equal to 10/3. And then I'm going to subtract the 4/3 on both sides. So log base 2 of x equals 10/3 minus 4/3, which is going to give you 6/3, which is 2. And then when you get here, I'm going to do circle of life. I'm going to convert. So 2 to the second power is going to be your x value, which in this case, we're going to have an x value of 4. And then, of course, lo and behold, you're going to take your x value, because we are dealing with a logarithmic equation, and you need to plug it in to check to see if it's going to be extraneous. So if I just plug in 4, it's positive, we're good to go. So 4 is a legit solution. So that's a good problem. Speaking of good problems, but also terrible, 30. So I did this one already, and I'll just give you a precursor. It's a little lengthy, but I'm going to take some shortcuts. So starting off, so I have log base 3 and log base 27. So I'm going to rewrite the base of 27 as a base of 3. So I'm going to have log base 3 of x minus 2. And then, of course, I want to rewrite it as log base of 3. So log, I like to write my new base in red. And then your argument in the numerator is going to be your original argument. So 4x plus 7 over the argument in the denominator, which is going to be your original base. So we're going to have log base 3 of 27 in the denominator. So I can actually rewrite log base 3 of 27. So this would be log base 3, that's a 3, of x minus 2. And that's going to equal log base 3 of 4x plus 7. And then 3 to what power gives you 27? Well, that's just going to be 3. So log base 3 of 27 just gives you 3. 3 to what power gives you 27? Okay, now I'm going to multiply that 3 over. So now I have 3 log base 3 of x minus 2. And that's going to equal log base 3 of 4x plus 7. And then based on power property, I'm going to move my coefficient of 3 to the exponent. So now we're going to have log base 3 of x minus 2 cubed equals log base 3 of 4x plus 7. So now that I have single logs on both sides, I'm going to take my arguments, can't forget the 3. I'm going to take both of my arguments and just set them equal. So I know x minus 2 cubed is going to be equal to 4x plus 7. So when you get here, you are going to need to expand x minus 2 cubed. So here's a little flashback for you. We're going to do binomial expansion, or binomial theorem. So we're going to have to use Pascal's triangle. So if you remember, so 1 in the top row, then 1 and 1, then 1, 2, 1, 1, 3, 3, 1. Because remember, your 3 tells us what row we want to go to. Because in Pascal's, remember, we start in row 0, and then row 1, and then row 2, and then row 3. Okay, so when I expand, I'm going to have my first value is going to descend in power. My second value is going to ascend in power. So I'm going to use coefficients of 1, 3, 3, 1. So this is going to be 1, 3, 3, 1. So my value of x is going to descend in power starting at 3. So I'm going to have x cubed, and then x squared, x to the first, and then x to a 0 power. And then my second value, so negative 2, is going to ascend in power. So I'm going to have negative 2 raised to a 0 power, negative 2 raised to the first power, negative 2 raised to the second power, and then negative 2 raised to the third power. And then we want to add all these values together. So when I get here, this is going to be x cubed. 3 times negative 2 is going to give me negative 6x squared. And then negative 2 squared, which is positive 4. 4 times 3, which is going to give me 12x. And then we have negative 2 cubed, which is going to be negative 8. Yep. So that's what I'm going to rewrite or fill in over here. So now I'm going to rewrite it as x cubed minus 6x squared plus 12x minus 8, and then that equals the right side, which is 4x plus 7. And now I want to move everything on the right side. I want to move it to the left side. So I'm going to subtract 4x, and then I want to subtract 7. That's a 7. I told y'all this problem's long. So we're left with x cubed minus 6x squared plus 8x minus 15. So now we need to find the values that make this equation true. Now, when I have a cubic, what's going to happen is we're going to have to do rational root theorem. So rational root theorem, lo and behold, we want the factors of p over the factors of q so that we can find the possible values or the possible solutions. So let me do this up here. You're coming with me. 3 dots. Bye-bye. So my factors or my possible solutions are going to be all the positive and negative factors of p over all the positive and negative factors of q. So I want all the factors of 15. So we have plus and minus 1, plus and minus 3, plus and minus 5, and plus or minus 15. All over the factors of q, which is just going to be plus or minus 1. So what's going to happen is you're going to go value by value. So negative 1 and do synthetic with 1, negative 6, 8, and then negative 15. And we're looking for a remainder of 0. If I get a remainder of 0, that's how you know that the solution works. So this is where I'm going to take a shortcut because I don't want to test every freaking value. So I'm going to cheat. I'm going to just say that the actual value is 5. So we're going to pretend that we tested all the values. I'm going to come over here and try 5 for synthetic. So when I do 5, we're going to get 1, negative 6, 8, and negative 15. So I can do synthetic. So bring down the 1, which is 5. Add, and you get negative 1. Multiply, you get negative 5. Add, you get positive 3. Multiply, you get positive 15. Add, and you get a remainder of 0. So that's what we want. So if I have an x value of 5, that tells me that this equation over here would be written as x to the 0 power, which is my constant, then x to the first, and then x to the second. X equals 5 as a binomial would be written as x minus 5. So when I rewrite, this is going to be the same as x minus 5 times my equation here, which would be x squared minus x plus 3. And then when you get it down to a quadratic, then you want to be able to factor or find the solutions to this quadratic. So I'm going to do the discriminant. So I want to see if I even need to do quadratic formula. So when I do the discriminant, that's b squared minus 4ac. If it's greater than 0, we have 2 solutions. If it's equal to 0, we only have 1 solution. And if it's negative, then we have no real solutions. So I like doing the discriminant just because that kind of gives me a heads up as to what exactly I'm looking for. So when I do the discriminant, so I'm going to have my b value, which is negative 1 squared, minus 4 times my a value times my c value. So this is going to give me 1 minus 12, which is negative 11. So we have no real solutions on this one. So that's just for the quadratic. So what that tells me is I would just disregard the quadratic, which means my only solution here would be x equals 5. But of course, because it's a logarithmic equation, I have to go back and plug it in to see if it's extraneous. So if I do 5 minus 2, we get positive 3, which is good. And if I plug it in over here, 4 times 5 plus 7, we get 27. It's positive, we're good. So 5 is the only legit solution that we're going to have over here. The quadratic would not give us anything else. So that's the first video. Next video is going to be inequalities.